Okay, so Don, you've talked about the economies of scale in the beta here. What about for other components?
Well, great question, Bill. Right now I'm thinking of two kind of classic studies that have been made of the costs of different water system components, pipes, water intakes, wells, elevated storage tanks, treatment plants, pumping stations, that sort of stuff. And probably the most reliable data that I know of, and I've been away from this business a little while, was a study that was conducted by the U.S. Environmental Protection Agency. It's in Figure 4, I'm pretty
So
sure.
we can give the reference to the students.
Right,
Yeah,
right,
okay.
Okay. And in that study by the U.S. EPA, it was a gigantic study. They had thousands and thousands of data points for different components, each component of the systems. So it was pretty good reliability. All of the cost equations for predicting costs are the same log linear models with cost on the left-hand side and some capacity indicator on the right-hand side. And in component after component, irrespective of the kind of component, the exponent of the hydraulic capacity of the system is a number between 0 and 1. And it's usually in the ballpark of 0.6 or 0.7. Chemical engineers have done a lot of work in this field with cost functions for different manufacturing facilities. And they talk about the 0.7 rule being the exponent of the capacity of the system has a numerical value of about 0.7. And we know that if the exponent of these log linear functions, these power functions, if the exponent of the variable that reflects capacity of the system is between 0 and 1, the function is concave. It reflects economies of scale because the average cost decreases as the capacity or scale of the system increases. And it's remarkable in the EPA report that the exponents are in the order of 0. They can get to be as low as 0.5. That would reflect very large economies of scale. An exponent of 0 would be a perfectly flat fixed charge function, tremendous economy of scale. So 0.5 to about 0.7.
So do we ever have diseconomies of scale in water and sewer systems?
Let's go back to the water systems. They're easier to deal with. There are always economies of scale with respect to the hydraulic carrying capacity. That's just the nature of pipe. I said to you that a 6-inch diameter pipe has twice the flow carrying capacity as a 4-inch diameter pipe. So with respect to the flow carrying, the hydraulic capacity of the system, there are always economies of scale. How about, we're talking about water now, how about the length of pipe? Are there economies of scale or diseconomies of scale? Let's think you and I have worked in a bunch of countries. Right now I'm thinking of Ghana, where in Kumasi, most of the households were in buildings that had four or 5 stories to them, maybe 6 stories to them. It doesn't, in that kind of a community, it doesn't take any more length of pipe to bring water to, let's say, 20 or 50 households that are in the same building as it would to serve a single household. So there are large economies of scale with respect to the length of pipe where we have multi-story buildings for housing purposes. Let's think about now a situation where we have a geographical area that the network is going to serve, still thinking in terms of a water system. But now maybe the mayor of the town, maybe he lives 10 kilometers out of town. And now this guy is saying, hey, I want to be served with this system. Mm-hmm. Oh, okay. So to bring a very, very small additional quantity of water to serve the mayor, large economies of scale with respect to hydraulic capacity, but to extend the pipe 10 kilometers to serve one household, I'm sure that the cost of that extension, the marginal cost, is very, very high. That's going to pull up the average cost. There are diseconomies of scale. So, and the way this plays out, especially with sewers, Dale, is that as we move away from the more densely populated parts of a city, where there are economies of scale with respect to both hydraulic capacity and the length of pipe that goes into the system, because the households are close together or they're in multi-story buildings. As we move to the fringes, the peri-urban areas where the population densities are low, then there can be diseconomies of scale with respect to the length of pipe. And that's where networks typically stop. And engineers may or may not have some thumb rules that they use for how far should we extend the pipe network into rural areas.
Can you explain what you mean by thumb rules for our students?
They may say, if the households are more than 30 or 50 meters apart from each other, the length of pipe to serve an additional house, pretty long, and the average costs of serving households in such a sparsely dense, sparsely populated area are going to be very, very high. The thumb rule would be don't extend the pipe network to areas or neighborhoods where housing, the distance separating the households is any more than 30 or 50. This gets played out, especially in industrialized countries, with respect to when do you switch from septic tanks to a pipe sewer system. Septic tanks are on-site wastewater treatment systems or disposal systems. So their costs are independent of housing density. Everybody has their own separate system. But septic tanks, after a while, are going to fail. What happens is it is the drainage fields that fail with these. Water sewage starts to pond on top of the ground. Kids play in it. It becomes a threat to health. And that's when usually the public sector comes in and says, we're going to build pipe sewers. But what happens in those areas if the housing density is still very sparse? Big time diseconomies of scale to serve them. That sometimes happens, not so often in developing countries, because it's really just too costly. So developing countries frequently will say, okay, let the kids, we're going to turn a blind eye to the health implications here. Let the kids play games in the sewage that's on top of the ground. So, which is really deplorable. I mean, it's heart-wrenching. Yeah.
Don, you remember our students are, most of them are not engineers, so, they're not going to know all about all the details of the cost functions. But I want to come back to some big questions about sort of cost in serving households in developing countries. First, sort of how different are the costs in industrialized countries, say New York or London, from cities in developing countries, Mumbai or Tegucigalpa or Accra? What kind of factors determine the differences in cost between industrialized and developing countries?
Well, the thought that immediately comes to mind, Dale, is that in the industrialized countries, lots of rules and regulations, lots of permits that need to be obtained before a contractor can come on the scene and build anything. Lots of rules and regulations in the bidding process, which means that the bids that contractors in industrialized countries submit, they're going to be more expensive than in developing countries just by virtue of the regulations that exist in the industrialized countries. But beyond that, I think that developing countries, even in large cities like Delhi, like Metro Manila, big places where you and I have worked, that it's easier for contractors to do business by getting their equipment onto the site than in a place like New York City, where, for example, there may be more vehicles. So traffic control or the construction of temporary roads while we're tearing up a main highway to lay down a water or sewer system on the edge of that highway in a right-of-way, all that traffic in an industrialized country has to be rerouted someplace else. A few years ago, Dale, the value of alpha in the pipe cost function was somewhere around maybe $15 if diameter of pipe was measured in inches. What does that mean? Let's go back to that function that we were talking about. It is cost per unit length is equal to alpha diameter raised to a beta. Let's assume that the value of diameter is 1. 1 raised to anything is still 1. So alpha, what it stands for, is the cost per unit length of a piece of pipe that has diameter 1 inch, assuming that we've measured diameter of the explanatory variable in inches. All right? That's around $13, $15. It's probably a good deal lower than that. Maybe, no, it's probably a mistake for me to say good deal lower than that. Certainly it's going to be lower than that in rural areas. So I wouldn't be surprised in rural areas, or it's not really rural because rural areas are not going to have a piped water supply system, but in a small town, for example, I wouldn't be surprised that they could find numbers that would be under 10. Okay, maybe between 5 and 10 if they measure diameter.
Now you've introduced this notion about urban and rural. What can you say about sort of differences in cost in rural areas and urban areas in developing countries?
Oh, in developing countries, the rural construction costs in rural areas in general are going to be much lower than in the urban areas. So I don't have any numbers, Dale, that I can toss out. But
that's
here's a consideration for, I think, people, for maybe your students who will be working in rural areas in developing countries with mostly piped water supply systems, not so much piped sewerage systems. In a country like the Philippines, small town after small town are what I call linear systems. They develop along a major highway, and they're laid out along a major highway. So if they're going to have a pipe system, whether piped water supply or piped sewerage, if it's a pretty big town, they need a lot of pipe because the community may only go one road back from the main road. The word that engineers use for these pipe networks is they're not reticulated. Reticulated being interconnected pipes that are in close proximity to one another that surround blocks where people live. So there are a number of, and in my experience, a number of communities, especially in places where I've worked in Southeast Asia, for example, but you find it in Africa as well. These linear communities, sometimes their costs will be out of kilter with the costs of that one finds in industrialized countries because they're linear systems laid out for long distances along roads. There are lots of vendors that are doing business along the roads. You don't find that in the industrialized countries. So, and even in developing countries, some small towns can be very compact. You're not going to find linear systems in mountainous areas, for example, right? So it's really hard to generalize on this stuff, Dale. And it's why we started this conversation by talking about the nature of the systems that we're going to model. So people have to think about if they were actually going to submit a construction bid on the system, how would those construction bids change from one kind of system to another? If they would find it very difficult to think about how can I estimate the cost of this for submitting a bid, chances are it's not going to be very easy to model that system.
But most of our students are not going to be presenting bids, though, but I would like them to know sort of something about the cost per cubic meter of piped water systems and maybe cost per cubic meter for water and sewer. So, when they're looking at cost data, and they see, X per cubic meter for serving a community in a developing country, what should surprise them and what X would not surprise you?
These are great questions. And You're asking questions. You're asking me to generalize. I'm never very good about generalizing. My head just doesn't work in terms of generalities. But I think after decades of doing this kind of work, both you and I pretty much agree that a well-run water supply system these days, the entire cost of operating that system, and this includes the cost of recovering the capital costs of constructing, that those costs are in the order of maybe $1 per cubic meter.
That's just for the water.
That is just for water. Now, what do we think? Is sewerage going to be higher or lower? Because sewage runs downhill. The smallest diameter pipe in a water supply system is probably 2 inches in a developing countries. In the United States, it's 6 inches. Right? The smallest pipe in a pipe sewer system is 8 inches. So right away, the pipe is much larger diameter. It's much harder to construct. The pipes have to be laid on grade so that they're running downhill. So I would expect that the cost of a well-run sewerage system could be twice as high. It could be $2 per cubic meter.
That includes the wastewater treatment.
So that would include the whole ball of wax.
Yeah.
That would be including
Right.
treatment, and the operation of a well-run system. One of the reasons why it's difficult to make these generalities is that there's great unevenness in developing countries in maintaining the systems, especially when the infrastructure is is underground. It's out of sight. You don't see it.
But that's true in industrialized countries
it is,
too, right?
but not so much. Even with pipe sewer systems, I mean, there are rules now. When I made reference to the regulatory commissions that watch over these municipal systems, these systems have to be. They're using cameras to inspect their sewers. They're reaming out their sewers on an annual basis. They're replacing sewers. That doesn't go on nearly to the same extent in developing countries. So I find it difficult to but I've given you some sense of the numbers.
Well, that's terrific, Don. Thank you so much for spending some time with us today.
It's been my pleasure.
That's great.
Thank you.